Hello everyone. In this particular lecture, we are going to see how a stable multivibrator can be used as voltage to frequency converter. So we know about a stable multivibrator operation and a stable multivibrator circuit analysis. All these things we know. So once again, I am drawing this stable multivibrator using NPN transistors. So in this way, the circuit is available. This is Q1 transistor. So this resistor is connected to collector of the Q1, that's why it is RC1, and this resistor and capacitor are connected to base of Q1, that's why this is R1C1, and this transistor is Q2, so this resistor is RC2 since it is connected to collector, and this resistor is R2 and this capacitor is C2 since these two are connected at the base of the Q2. So in this way we have the stable multivibrator circuit. So what is the operation? Simply I will revise that one here. You assume that Q2 transistor is in the off condition and Q1 transistor is in the on condition. So the capacitor which is just above this on transistor will be starting the charging. So C2 is eligibility for charging purpose. C2 will be charged from VCC. Okay, C2 will be charged from VCC through R2 and Q1. While it is charging, when Vc, that means capacitor voltage is equal to V gamma, that is equal to base voltage of Q2 transistor, then Q2 will become on. When Q2 is becoming on, what will happen? The collector voltage of Q2 transistor, it is changing from VCC to VCE sat. That means VCE sat is coming from VCC by having the voltage drop IC and RC2, IC into RC2. By the KVL at the output we can write. Okay. So whatever the sudden voltage drop is there, that is IC RC2 will be sent to base of the Q1 transistor through the capacitor C1. So now VB1 will become negative because of the drop. Okay, drop by how much amount? IC into RC2. Okay, so it is becoming negative means Q1 will become off. When Q1 is off, VC1 will become VCC. Okay, because for the off transistor we know the collector voltage in this particular circuits will become VCC. Okay, so that is what we have seen. Now what happened? Initially we have taken Q1 is in the on state and Q2 is in the off state. Now we got Q2 is in the on state and Q1 is in the off state. States have been changed. Now since Q2 is on, the C1 capacitor starts charging and the process will be repeated again and again. So the transistors automatically will be getting on state, off state continuously like this. And we have taken the time period derivation capital T. For that first we have to understand the waveforms. So see carefully. So I am taking here collector 2 voltage, base 2 voltage, collector 1 voltage, base 1 voltage. So we have taken first Q2 is off, then it is becoming on, then again off, on, off, on. Next VB2 is first negative, then it is becoming on, off, on, off, on. Collector means here Q1 transistor opposite way we have to take. Like this we have to take. And VB2 on state, off state, on state, off state, on state, off state. So anyhow, here very important point is, here round off is there. Whenever it is changing from on state to off state, here you can able to observe the round off. Because of this same thing, here you will get this type of structure, overshoot you will get here. Okay, so anyhow I am not going to discuss in this particular lecture about that particular overshoot. We'll see that one later. Now our intention is the derivation of the time period of the output. But if you see, the time periods of all these four waveforms are equal, and we are going to use here capacitor voltage to derive the equation of the time period. Why? Capacitor voltage is equal to base voltage only, because you can see in the circuit the base voltage of Q1 and Q2 are connected to capacitor voltages only. That means base voltages are nothing but capacitor voltages only. So we know very well about the capacitor, that is Vc of t is equal to V final plus V initial minus V final into e power minus t by Rc. This is the formula. When you consider only this one, what will you get? You will get T1 time period, and here T2 is there. So to get T1, okay, first what we need to do? Its initial value is this one, its final value is this one. Initial is this one. This is final. So it can charge up to which value? It can charge up to VCC. We have given the statement that the capacitor C1 or C2 will be charged from the supply VCC. For example, if you take C2, it can be charged from VCC through R2 and Q1. So it is charging from VCC means without having other elements, it can charge up to maximum supply voltage, that is VCC. So V final is equal to VCC. What about V initial? If you see here already, just before this one you have VB sat. From the VB sat there is a sudden drop is there, that is IC into RC2. This is what you need to observe. So this is a sudden change. But this IC into RC2 can be written from the output KVL equation like this. Okay, VCC is equal to VC sat plus ICRC. This is the output KVL equation. Output KVL. Then you replace this ICRC in the above equation with this equation. Then VI will become VB sat plus VC sat minus VCC. Okay, so V final is ready, V initial is also ready. If you are talking with respect to C2 capacitor, so time constant tau 2 is equal to R2 C2. Okay, so now I am using the capacitor voltage equation. V final is how much? VCC plus V initial is how much? VB sat plus VCE sat minus VCC. Okay, and V final is again minus VCC e power minus T1 by RC. When you take T is equal to T1, this voltage will become V gamma. You see, by the end of the T1 seconds, its voltage will become V gamma only. Capacitor voltage or the base voltage is becoming V gamma. That's why I have equated this one at T is equal to T1, Vc of T is equal to V gamma. Send this VCC left side, that is V gamma minus VCC we will get. And here very important point is VB is at plus VC is at is actually approximately equal to 2 times of V gamma. You can check it with the practical values. So here 2 times of VCC is there. So if you take 2 common, V gamma minus VCC into e power minus T1 by RC. So this one will be cancelled. Send this e power minus T1 by RC to the left side. So it will become e power plus T1 by RC. It is equal to what we will get now? 2. Take natural logarithm on both sides. Then finally you will get T1 is equal to 0.69 RC. This is not complete time period. It is half of the time period only. So this portion we have calculated. Okay. And if you take this is nothing but due to R2C2. Tau 2 is equal to R2C2 I have given. Na? So T1 is equal to, you can take 0.69 R1C1 or R2C2, whatever it may be. In a similar procedure, you can get T2 is equal to 0.69, for example, R1C1. So total time period is equal to how much now? I am going to the next slide. That is T1 plus T2. T1 means 0.69 R2C2 or R1C1. So if you take 0.69 is common from T1 and T2 formulas, 0.69 into R1C1 plus R2C2. If you take R1 is equal to R2 is equal to R and C1 is equal to C2 is equal to C, this is equal to 1.69 into 2 means 1.38. 0.69 into 2 means 1.38 into RC. So in this manner we will get, if you want frequency, 1 by time period. So just getting this equation is not enough, you need to understand that equation. So if you observe the circuit is involving, if you observe the circuit is involving 2 transistors, 2 capacitors, 4 resistors. Out of 4, 2 collector resistances are there and remaining 2 resistors R1 and R2 are available at the basis of the 2 transistors. Okay, and one DC supply VCC is available. But in the time period equation, which resistors are involved? Only R1 and R2. In the time period equation, if you observe 1.38 into R1C, this RC, or 0.69 into R1C1 plus R2C2, the resistances which are connected at the bases are involved in the generation of the time period but not collector resistances. That is what you need to remember. And one more thing is, this is independent of the VCC, because in this equation VCC is not available. Okay, so frequency we can take by taking the inverse of this one. So frequency also not depends upon the supply voltage VCC. Okay, so this is a general multivibrator time period equation or the frequency equation. Now specifically what we are seeing in the sense, voltage to frequency converter. Voltage to frequency converter we are going to see. For that, a little bit changes we have to made in the circuit. So 2 transistors we have taken as it is, Q1, Q2, and in a similar manner we are connecting the collector resistances R2, C2, and these are connected to the supply VCC. Till here everything is same. After that, what we are doing means, whatever the remaining connections are there, those are also I am taking. Listen carefully now. This connection should be connected to base of the Q2 and this resistor RC should be connected to the base of Q1. So in this manner we have given. So this is called R2C2 and this is R1, this is C1 because connected to base. Then now this R1, R2 are not connected to the same supply VCC. These are connected to the different DC supply capital V. This is the change we have made compared to the previous original Astable multivibrator. So where you will get the changes? If you understand the operation of the previous circuit, understanding this is very easy. Quickly I will tell that one. For example, Q2 is in the off state, Q1 is in the on state. So C2 capacitor should be charged. But charged from which supply? In the previous circuit, the C2 capacitor or the C1 capacitor will be charged from the VCC. But here VCC is not connected to that one. VCC, what is connected to the capacitor? V. That means C2 is charged from V through R2 and Q1. So if other elements are not available, the C2 capacitor can charge up to which value? Capital V. That means final voltage will become capital V. That is what you need to understand. Okay. And initial voltage is equal to, generally what we'll tell, VB sat minus, okay, how much amount of current drop is there? IC into RC2. Why there is no change in the initial voltage? You observe carefully. Once again I am starting the operation. Since we have taken Q2 is in the off state and Q1 is in the on state, C2 capacitor will be charged from the supply capital V through R2 and Q1. So since it is charging, the capacitor voltage will be increased. That means since it is connected to base of Q2, the base voltage is also increased. Whenever it is reaching V gamma, Q2 transistor will get in the on state. When Q2 is becoming on state, its voltage will be changed from VCC to VCE sat. Okay, that means how much fall down is there in the voltage? Minus IC into RC2 drop. This much amount of drop is there from VCC to VCE sat. But this sudden change in voltage will be applied to the base of Q1. Okay. So that what will happen? Previously it is VB sat. Now because of this particular operation, it is changed to VB sat minus this value. VB sat minus this value. So this is the initial value actually. So if you take the base voltage waveform like this. Okay. So at t is equal to T1, it reaches V gamma, but it can continue up to V, capital V. Now we cannot take the final value is VCC. Okay. Then this initial value is given by this particular value. Okay. VB sat minus IC into RC2. In this manner we can able to write. So final value is there, initial value is there, you can start calculating the capacitor voltage. So here I am writing capacitor voltage is equal to V final, that is capital V, plus V initial is how much? VB sat minus IC into RC2 we have to write. But from our previous knowledge, separately I will do here. From our previous knowledge, VB sat minus IC RC2, na, that can be written as VCC minus VCE sat. Like this we can write. This is VB sat plus VC sat, it can be written as 2 times of V gamma, okay, minus VCC. But here VB sat minus IC into RC2, that minus IC into RC2 itself we have written as VCC minus VCE sat. If you multiply minus inside, you will get like this, VB sat plus VC sat, that is equal to 2 times of V gamma minus VCC. So this entire thing is nothing but what? Just VI. Okay, so I am writing that one. So V final plus V initial means 2 times of V gamma minus VCC minus V final, that is V, not VCC. Okay, so e power minus T by R2C2. When you take T is equal to T1, this VC of T will become V gamma. By the completion of T1 seconds, it will reach V gamma. So V gamma is equal to V plus 2 times of V gamma minus VCC minus V e power minus T1 by R2C2. Okay. If you neglect V gamma in comparison with the other voltages, then what we can write here? Minus V is equal to this V gamma means 2 times of V gamma is also neglected. So here minus of VCC plus V will be there, e power minus T1 by R2C2. So this minus will be cancelled. You can send this exponential to the left side. So e power T1 by R2C2, that is equal to, if you divide with V, 1 plus VCC by V. Okay, if you take natural logarithm, T1 is equal to R2C2 ln of 1 plus VCC by V. This is just T1. Similarly, T2 also we can write. First T1 I am writing once again. That is R2C2 ln of 1 plus VCC by V. R2C2 ln of 1 plus VCC by V. Similarly, T2 is equal to R1C1 ln of 1 plus VCC by V we will get. Okay. So if you take R1 is equal to R2 is equal to R, C1 is equal to C2 is equal to C, T1 plus T2 is equal to capital T. So capital T is equal to, what will you get? 2 times of RC ln of 1 plus VCC by V. If you need frequency, that is equal to 1 by T, 1 by 2RC into ln of 1 plus VCC by V. So like this we'll get. So what is the advantage of doing this one compared to the previous original circuit? Here what is the main change we have made? Instead of connecting R1 C1 to VCC directly, we have connected to the new supply capital V. Because of this same derivation, if you apply, the frequency you are getting in terms of capital V, and that is anyway supply, VCC is supply. So in terms of capital V got. So based upon the capital V, now the frequency is decided. Now the frequency is decided by capital V. That means voltage to frequency conversion is possible using this particular Astable multivibrator. Okay. So in this manner you need to understand the operation. If you understand the operation perfectly, then only the further topics can be understood very easily. Thank you.